Hey everyone, welcome back. Today we're diving into some really cool research that gets at one of the biggest headaches in AI. How do you create an AI that doesn't just shatter when things go wrong? One that can actually adapt and recover, instead of just being perfect in a perfect world. So how do they do it? Let's get into it.
So check this thing out. This is the R-Hex hexapod robot. Now, using some pretty advanced algorithms, we can teach this little guy literally thousands of different ways to walk. It can go fast, it can go slow, it can step really high, you name it. It's honestly an incredible showcase of what modern AI can do, creating this massive library of skills for pretty much any situation.
All right, but here's the million-dollar question. What happens when the real world happens? A leg stops, or the ground underneath it suddenly turns to sand. Well, all those thousands of walking styles that were perfected for a six-legged robot, they're suddenly worthless. The robot might just freeze up, or worse, just fall over completely. It's game over.
This is what researchers call the brittleness problem. See, when we train an AI to be the absolute gold medal winner at one very specific thing, it often becomes incredibly fragile. The second the world throws it a curveball it wasn't expecting, the whole system can just fall apart. So how do we build an AI that can bend instead of break? Well, the first piece of the puzzle is to just think about the problem differently. A standard algorithm, right? It's always trying to find that one single best perfect solution, the gold medal. But a quality diversity algorithm, or QD, does something else entirely. Its goal is to find lots of good solutions that are also really different from each other. It's not looking for one perfect key, it's building a whole toolbox. So this QD algorithm gives our robot this huge library of solutions, a massive collection of different ways to walk. But let's be honest, having a giant, messy toolbox isn't super helpful when you're in a jam. You'd waste all your time just looking for the right wrench. You need a system, a way to find the right tool and find it fast.
And that system has a name. It's called a behavior space. The best way to think about it is like putting labels on the drawers of that toolbox. So one drawer is labeled super fast walking, another one is super energy efficient, and maybe another drawer is labeled stable but kind of wobbly gaits. That way, when the robot suddenly damages a leg, it knows exactly which drawer to pull open to find a new way to get around.
Okay, but that just leads to the next big problem, doesn't it? Who writes the labels? I mean, how do you create the perfect labeling system for this toolbox? A human expert could try their best to figure out the most important behaviors, but what if they miss one? What if the best way to organize the tools isn't obvious? How do you design the perfect system for thousands of solutions? And this is where the big breakthrough from researchers Bossens and Terrapore comes into play. Their system is called Quality Diversity Meta-Evolution, or QD-Meta for short. And get this, instead of just evolving solutions for the robot, it evolves the rules for organizing those solutions. It's an AI that is literally learning how to learn. So here's how this meta-evolution thing works. First, the AI comes up with a whole bunch of different rule books. Think of these as different ideas for how to label the drawers of our toolbox. Then, for each one of those rulebooks, it quickly builds a library of behaviors. Next, and this is the clever part, it tests the entire library against a high-level goal that we give it, something simple like survive leg damage. The rulebooks that create the most useful libraries for that goal, they get to reproduce and create the next generation of even better organizational systems. It's evolution on top of evolution.
The researchers themselves put it perfectly. Basically, their big idea was this. If you tell the AI that its main job is to create a toolbox that's really good at handling surprises, then it will automatically figure out the absolute best way to organize that toolbox. So the big question is, did it actually work?
To find out, the researchers put QD-Meta head-to-head against some other state-of-the-art methods in a couple of really tough challenges. The first test was this complex math problem where the rules could change without any warning. Now, take a look at this graph. When the problem changed, the other algorithms, that's the green and red lines, they took a while to find a decent new answer. But QD-Meta, that's the blue and orange lines, wow, it found a near-perfect solution almost instantly. Its library was already built and organized for exactly this kind of surprise. But the robot tests were even more amazing. When the high-level goal was get good at handling obstacles, QD-Meta evolved a whole library full of these jumpy gaits perfect for climbing over stuff. But when they changed the goal to get good at handling leg damage, it created a totally different library, this time full of stable, even if they were a little wobbly, gaits. It automatically tailored the entire library of solutions to whatever the user needed it to be robust against. And here is a wild, totally counterintuitive result. The other methods,
They generated these gigantic libraries with 3,000 to 4,000 different controllers. QD Meta, on the other hand, produced this lean, super-focused library of only about 100. And it turns out, you don't need more solutions. You need the right solutions, organized perfectly. This smaller, curated library made finding the right skill way faster and more reliable.
So what does this all mean? What's the big picture for the future of AI? Why is this research such a big deal?
Well, this approach really gives us 4 major breakthroughs. First, it creates solution libraries that are tailor-made for a specific purpose, like safety or robustness. Second, because it produces smaller libraries, they're safer and more transparent. We can actually look at all 100 solutions and understand them. Third, this enables unbelievably fast adaptation to surprises. And critically, it does all of this automatically. You don't need a human expert sitting there for months trying to design the system by hand.
This work really opens up a brand new and honestly a much more powerful way of thinking about how we build AI. So I'll leave you with this final thought to chew on. What happens when our AI doesn't just solve the problems we give it, but starts evolving entirely new ways of solving them?